Good morning everyone, I'm David Nicholls. Welcome to sunny Canberra. I'm sorry I can't be at Abbazia. I'm a postdoc at Mount Stromlo working with Lisa, Ralph and Mike. At the moment I'm working on photoionization modelling, mainly of H2 regions, using the Mappings photoionization modelling system, which some of you know and either love or hate. This talk was recorded a few days ago, your time, so if you have any questions, we can hook up via Skype and I can answer the questions in real time. It's about 9 AM Thursday where you're watching this and 5 PM here, if we're sticking to schedule. Slide 1, in which we see Mike in magistral mode from the conference poster. This is the first time I've tried anything like this video. It's entirely experimental, so we'll see how things go. Fingers crossed. And now for the talk. Abundance scaling in nebular models. The talk is based on our paper in MNRAS from last year, Nicholls et al. 2017. You can find it on ADS. Slide 2. What were our motivations for this work? Well, if you're familiar with photoionization modeling, you'll know that there are several inputs into any model system. The atomic data, stellar atmosphere models, stellar evolutionary tracks, as well as the physical parameters such as pressure, ionization parameter, and so on, and of course, the physics. Underlying this is the standard or reference abundance scale. Until now, the convention has been to use the solar abundance scale. It is a key input not only directly into the model, but also in the stellar atmosphere models and the stellar evolutionary tracks. And herein lies a problem. Over a dozen solar scales have been published over the past 40 years. Different standards underlie components we use in the photoionization modeling. For example, Paul Dreck's WM basic stellar models are based on the Anderson-Greves solar scale from 1989, whereas the Geneva stellar evolutionary tracks are based on more recent solar scales from Astronomy et al. These differ by a factor of 2 in oxygen abundance, which, if you consider how important oxygen is in nebular modeling, is a bit of a worry.
Slide 3.
Stellar atmosphere and evolutionary tracks are used to build population synthesis models to create the spectra that ionize and excite the nebula. Generating synthesized cluster spectra using programs like Starburst 99 and SLUG2 is consequently problematic, given that the inputs are inconsistent, but we do the best we can. Slide 4. Perhaps the most important consideration is how the nebula elements scale at metallicity substantially below the standard. We know that simple linear scaling of the standard abundances is wrong. If you have a nebula with an oxygen abundance of 1/10 solar, the ion abundance is not 1/10 solar, but less than that. So simply dividing each element abundance by a common factor is wrong, yet this has been done quite a bit in the past. Enrichment of the interstellar medium depends on the star formation history at earlier epochs and the nature of the supernovae that were responsible for the enrichment. Slide 5. If we wish to look at stellar abundances as a guide to past nebular abundances, which we do, we face the problem that measured stellar abundances are referenced to iron, whereas nebular abundances are referenced to oxygen. As these don't scale together, translating between the stellar and nebular abundances is difficult. So how do you translate between the two scales? Do the twain meet? The answer is yes. The good news is that we've worked out how to do it. It's quite simple. Slide 6. So what did we do? The first step was to identify a standard reference abundance set that was not tied to the continually evolving solar abundances. Using any particular solar data set leads to temporal incompatibility with earlier and later work. So we adopted a scale suggested by Nieva and Przybilla in 2012, which drew upon measurements of an ensemble of 29 main sequence B stars in our region of the Milky Way. These stars are young and nearby, and their photospheric abundances are a good measure of their bulk abundances, and thus the abundances of the nebulae in which they were born. A side point, Asplund et al. 2009 provide an abundance set that is widely used in stellar and nebular analysis. Unfortunately, there are 2 sets of abundances reported in that paper, the photospheric abundances and the bulk or protosolar abundances. The difference between the oxygen abundances is small, but helium is another matter. The solar photospheric abundance of helium is only a little above primordial, which is obviously wrong given the Sun was born 8 billion years or so after the Big Bang. The bulk abundance of helium from the Asplan paper is a more reasonable value and close to the B-star's value. The first of these is most often used, but it's the second one that should be used. Yet another difficulty. Slide 7. The Neva and Principilla B-star abundance list only includes elements that could be measured in stellar atmospheres. So we augmented their list with the best available data from other sources, including the Sun, nebula measurements, and Katerina Lauder's meteoritic data. The resulting composite list we refer to as the Galactic Concordance Scale. The next exercise, and much the most important, was to determine the relative abundances at lower metallicities. To do this, we drew on a large number of stellar abundance measurements from main sequence unevolved stars, published over the last 20 years with log iron abundances, that's log Fe on H, as low as -3.
Slide 8.
We used the behavior of element abundances in these main sequence stars as a guide to how abundances scaled in the H2 regions in which they were formed. In other words, we use them as fossil record of the H2 regions. There are some very clear repeating patterns in the element abundances, as I will show shortly. From these we are able to derive simple scaling relationships for the key nebular elements. Slide 9. These scaling relationships express the abundance of each element as a function of iron abundance. One of these was the oxygen abundance, expressed as log O on Fe. By simply inverting this ratio, minus log in other words, and adding the result to the other iron-based log ratios, we can convert them to ratios to oxygen. This gives us a way to scale the abundances of all the important nebular elements as a function of total oxygen abundance. This is immediately useful for nebula modeling and is as an input to mappings. So, what happens when we use these scaling relationships? The results are very encouraging. Slide 10. This plot shows the results of the different scaling processes in mappings photoionization models of H2 regions. It is a BPT type diagram, here log O3 on H beta versus log N2 on O2. The white points are from the Sloan data release 5. The vertical spray arises from active galactic nuclei, but the main diagonal region is principally from H2 regions. There are two grids overplotted, generated by mappings. The yellow grid shows the result of simple linear scaling, that is, dividing each abundance by the same factor, which we know is wrong. It doesn't match the Sloan data very well. The second red grid shows the result of our new nonlinear scaling. The improvement in the fit to the data is obvious. We're very happy with the result, and the Galactic Concordance Standard and the nonlinear scaling method are now default in mappings. Slide 11. Where did these scaling relationships come from? This plot shows the stellar abundance data from different surveys, the colours corresponding to the papers in which the data was published. These plots are for three alpha elements: oxygen, magnesium, and silicon. Some elements are easier to measure than others. Oxygen is derived mainly from two lines, 6300 angstroms and 7770 angstroms. The first of these has problems with the oxygen airglow. The second experiences interference from two nearby stellar Nicholls lines. However, this dataset is exceptionally well curated and reduced by Abbazia et al. Using 3D and LTE, and is about the best oxygen data currently available. Magnesium and silicon, on the other hand, are much easier to measure in stellar spectra, even for faint M dwarfs. You'll notice there is a consistent pattern which can be modeled by piecewise linear fits. The first trend at low iron metallicity is constant. This is where type 2 core collapse supernovae are generating the enrichment. Then we reach a point where the type 1a supernovae cut in, which in the Milky Way is at an iron abundance of log Fe on H of -1. This marks a breakpoint, followed by a downward linear ramp through what we call the fiducial point. the here and now value, in other words. The ramp corresponds to the onset of type 1a supernovae and the consequent enrichment with iron. Following that, we have assumed a constant value of at metallicities above log Fe on H of plus 0.5. We don't know if this exists. I had a chat with Martin Asplund about this, and he said that it is plausible, but we don't know if it exists or not. We would need observations of unevolved stars at high metallicities to clarify the question. In any case, it's not important for nebula models, as any nebula that metal-rich will cool so rapidly that it is unlikely to be observed, except perhaps for the hydrogen lines. So we have a simple piecewise linear fit to the stellar abundance ratios. The characteristics are the level of the initial constant phase, the value of the log Fe on H at the breakpoint, and at the fiducial point. This makes modelling extremely simple. In these plots, the right-hand two panels show clearly the fiducial point as a yellow circle. It corresponds to the here and now value at the present day iron abundance. The plotted values are from the galactic concordance set. As you can see, they fit nicely in the middle of the observed stellar abundances. When you convert element abundances to oxygen ratios using the log O on Fe to log Fe on O inversion, you again obtain similar, very simple fits to the abundance of each element, but now referenced to oxygen. You might ask, what about the other non-alpha elements? Most behave similar to the alpha elements, and the iron series simply scale linearly with iron, just go straight across the graph. Again, these are simply converted to oxygen ratios. For some elements, there is very little stellar data, but these are elements which have no practical effect on photoionization models. You can see the plots for each individual element up to zinc in the paper. There are some, however, elements you don't normally see in main sequence stellar spectra, such as argon and neon. The next slide shows how we handle these. Slide 12. This plot shows the neon and argon as a function of oxygen this time. The two elements are not depleted into dust, so we can use the nebular observations to see how they behave. You will notice some white data points in the neon plot at the top right-hand corner. These are observations from some of the Nieva and Tabilla B stars. They are consistent with the nebular observations. Given the measurement errors, simple constant ratio versus oxygen abundance is justified. The same thing can be derived for other elements such as chlorine. See the paper for details. One more question arises, and this is shown in slide 13. How does the stellar data behave in other galaxies? We have data for the Large Magellanic Cloud and the Sculptor and Fornax dwarf spheroidals. This plot shows the magnesium to iron ratio. It's relatively easy to measure, even in distant, low metallicity red dwarf stars. It shows the Milky Way data in white, the same as data as before, but turned into monochrome to reduce confusion. The blue points are from the Large Magellanic Cloud, and the red points are from the Sculptor dwarf. The Fornax data is sparse, but generally similar to Sculptor. You can see that it is at least plausible to say that the same general pattern applies in terms of piecewise linear fits. Whether there is a breakpoint for the Sculptor stars is uncertain, but the scarcity of the data and its scatter do not rule this out. Finding very low metallicity M dwarfs at the distance of the LMC or the Sculptor dwarf is extremely difficult. So as a first approximation, we think it is possible to fit the same piecewise linear ramp model to other galaxies. The early enrichment ratio, the breakpoint, and the fiducial point will need to be determined for each galaxy. In the case of smaller galaxies, it is to be expected that the breakpoint will occur at a lower iron abundance than for the Milky Way, as there will be fewer core collapse supernovae and thus less enrichment before the type 1a iron enrichment begins. Therefore, the iron abundance is going to ramp up at lower metallicity than in larger galaxies. And in the absence of other evidence, we think that the Milky Way behavior is a good model for larger galaxies and probably for galaxies we observe at high redshift, which are also likely to be large. We think this is a useful method for photoionization model scaling, and it should be used in preference to simple linear scaling. We're looking forward to the release of the abundance data from the SkyMapper survey to see how it might affect our models. Step by step, we're improving the accuracy of our photoionization models, and it's encouraging to see They were able to model nebulae as well as we do, given the known problems with the inputs. And that's all I wanted to say about nebula modelling. I'll just finish off with a quick talk about Mike and me. I've known Mike for 30 years. The first 10 were when I was a bureaucrat, managing the bilateral science and technology program. This provided travel grants for international science collaboration. One thing I found was that astronomers are exceptionally good at finding sources of money and writing excellent applications to wheedle it out of government. I think the same is still true. My role as manager of that program was to deal with exceptions, to handle quality control, and to talk to the applicants to ensure they were making best use of the program. I got to know academics across a wide range of disciplines, although my background is in physics. My master's is in upper atmosphere physics, but I got to talk to a lot of people, not the least of whom were the astronomers. And that's how I got to know Mike. At that stage, he was enormously enthusiastic about Herbig-Haro objects. In fact, we were able to set up a major grants program that allowed Mike to work with the Space Telescope Science Institute in the early days of the Hubble, and that was really good. But 10 years later, the government changed, the program was abolished, and I left the public service. 10 years after that, after many life events, my wife, Linda, asked me what I wanted to do with the rest of my life. I answered that I had always wanted to finish off getting the PhD degree. What would you do it in, she asked. Astronomy had always been my passion, I answered. Where would you do it? I pointed out the window, that way, towards Mount Stromlo, which we can see from our house. Why don't you apply? No, I don't think so, I said. Linda disappeared to her computer for a few minutes, and she came back and said, applications close in a few days for admission for PhD studies. Why don't you apply? After a little thought, I replied, okay, I'll give Mike a call and see what he says. I also called Don Mathewson, whom I'd known since 1968, when I was at Mount Stromlo as a summer vacation scholar, and later worked for as a research assistant, before I headed off to Canada to study upper atmosphere physics. Both Mike and Don responded positively, so I submitted the application, and a few weeks later, a letter arrived telling me I had been accepted. Help! What do I do now? After checking around to see what PhD projects were in the offing, I decided Mike's idea was much the most interesting. It also meant I got to use the wonderful WIFE spectrograph that Mike had designed. My thesis was targeted at investigating the abundances in H2 regions in isolated dwarf irregular galaxies. 6 first author papers, several co-authored ones, including one with Luke. G'day, Luke. And 5 years later, I had completed the degree. Mike's wise guidance and irreverent nature played a big part in my success. Rather than apply for a Hubble Fellowship or something similar, I decided I was a bit too old for all that disruption. I am in fact the only PhD student of Mike's who is older than he is, by 6 months. Then Lisa offered to employ me as a postdoc, and I've been working here ever since, working with Lisa, Mike and Ralph. I've never enjoyed a job as much as this one. My only regret is that I didn't start it 40 years earlier. So I'll finish now, but I'd like to thank Mike for being an excellent supervisor, now a great colleague and a good friend. Thanks, Mike.